Today, I will be presenting the second in a three-part series of webinars addressing aerospace fuel systems modeling in Flowmaster. I'm going to start today's presentation with a brief overview of the benefits of using one-dimensional CFD software in the engineering process. We will then look at a review of the one-dimensional fuel system model for a typical two-engine passenger aircraft we used in the last session. After going over the base model in detail, we will add controllers and gauges in order to perform a new pair of transient case studies. One continues the theme of ground refueling from last time, and the second looks at fuel management during a complete flight from takeoff to landing. After the case studies, we'll discuss the next topics in this series and have a question and answer session. Risk is always a concern for companies, and usually, as a project progresses, the risks associated with a project tend to decrease. One of the main driving factors behind this is the increase in information that naturally happens as a project matures. By gaining knowledge very early in the process, designers and engineers can lower that risk even sooner. This is where upfront simulation can add significant value to the process. By allowing engineers and designers to investigate a growing number of prototypes virtually before any physical models are constructed, investment in upfront CFD can have significant value by lowering physical testing efforts later in the design. Because physical testing is time-consuming and expensive, virtual prototyping allows more variants to be examined in a shorter amount of time. Flowmaster fits into this idea because it is a one-dimensional computational fluid dynamics simulation tool that allows engineers to simulate complex thermofluid problems at a system level so that they can understand aspects of the design such as pressure, temperature, and flow rates throughout the design. Access to performance data early in the design process is always a challenge, but Flowmaster supplies built-in data from DS Miller out of the box to give you a baseline to work from. You can investigate both steady state and transient behavior in your systems, and you have the ability to simulate different types of fluids, including liquids, gases, refrigerants, and steam. There are also a host of specialty solvers for both complex phenomena like swirl and priming, or for making potentially repetitive tasks simple, such as performing a flow balancing analysis. Flowmaster has been helping its users meet these requirements for over 25 years across many industries throughout the world, including our focus today, the aerospace industry. Let's now take a few minutes to review what we did last time and expand on the basic model with the addition of controller and gauge components. Here is the schematic representation of the simplified passenger aircraft fuel system that we built in the previous presentation. The three large blue sections represent the wing and the center fuel tanks. The white boxes represent pumps, and the fuel feed and transfer plumbing is represented in green. Refueling lines are represented in dark blue. Shutoff valves are depicted throughout the model as the circular symbols indicating normally open or normally closed. And here is a Flowmaster system model drawn directly on top of the schematic image. It includes source components for our boundary conditions and extra loss components for items like filters and couplings. Again, the tanks do not take up the whole area outlined in light blue, but instead are single discrete components. The thin link lines represent a direct connection between adjacent components, but they're not pipes themselves. Nodes sit in the middle of the links and serve as convenient points to enter elevation data and interrogate flow results of temperature and total pressure. Let's look closely at one side of the aircraft model to take a closer look at what these components are and how they function. Looking in close detail on the left side, which is a mirror of the right, you can see how we have built our model out of individual components that stand in for their physical counterparts. The engine is modeled as a flow boundary condition attached to a simple shutoff valve. The cross-feed piping that connects the left to the center to the right-hand side of the aircraft is modeled as a series of basic pipe components. Two redundant mechanical transfer pumps submerged in the tanks are modeled with the rotodynamic pump component. A check valve is added to prevent reverse flow. The tank is modeled here using a 3-arm tank component that allows for 2 outlets and 1 inlet, but the 3 connections will act independently as inputs or outputs based on how the flow conditions in the model behave. This tank component can model heat transfer effects and has a simple compressible gas model for the ullage space. In the third part of this webinar series, we will replace this component with our advanced tank model to look into more detailed venting and inerting scenarios. For refueling and transfer between tanks, a shutoff valve, filter, and size transitions are modeled. The valve is a simple ball valve component that applies the built-in data from D.S. Miller's internal flow systems in the form of a loss coefficient versus valve position function. The filter is modeled as a generic discrete loss that can take non-dimensional loss coefficient or a function of pressure drop versus flow rate as an input. Piping to model the transfer and refuel gallery. And lastly, the refueling port, modeled as a flow source component along with another discrete loss to model the pressure drop across the refuel coupling and a filter screen. In the center of the drawing, we can see more detail of the components that we used in the model. Cross-feed piping and isolation valves are modeled with more elastic pipe and ball valve components. Center tank transfer pumps that feed directly into the cross-feed line or the refuel gallery depending on isolation valve position. 3-arm tank components, and piping to transfer fuel from the center tank into the refuel gallery to replenish the wing tanks during flight as opposed to directly feeding the engines. A similar filter and valve assembly makes up the refueling input to the center tank. And lastly, an APU is modeled, along with a shutoff valve at the aft of the aircraft. Like the engines in this model, the APU is simulated with a simple flow boundary condition. After the initial model was completed, we performed a series of basic steady-state and transient analyses to size piping and filter losses in an attempt to balance refueling flow. The main conclusion of the steady-state study was that when refueling from a single side, simple line sizing was not enough to ensure a balanced fill of the left and right fuel tanks. Actively controlled regulation was proposed as a possible solution. Here, we're adding a few different types of controller components to the model in an attempt to do that. Gauge components are added to measure tank levels, masses, and refueling flow rates, and controllers are added to open valves, control pump speeds, and provide a simple engine simulation. Proportional, integral, derivative controllers will automatically regulate the refueling flow to our tanks to a desired set point. And lastly, a master controller running a customized script that we will design will serve as the traffic cop and schedule the flow of fuel from one tank to the next. Let's take a closer look at how these controllers are used by applying them to a few case studies. The first study continues the topic of the previous webinar, refining our model to balance and schedule flow between individual tanks during a single-sided ground refueling event. As investigated in the previous session, the primary problem we are trying to solve is that single-sided refueling leads to a significant pressure difference in the refueling gallery, resulting in an imbalance in flow rate between the right and left sides of the aircraft. Additionally, the wing tanks are simply different in size and capacity from the center tank, and therefore the wing tanks become full in different amounts of time than the center tank does. We previously investigated adding passive flow restrictors and increasing the gallery line size to physically balance the flow. This resulted in issues with high pressures, packaging concerns, and would require fueling from either only the right or the left-hand side by design. By adding active control, we strive to be able to balance and schedule our flow regardless of which side the aircraft is being fueled from. We can divide active control into 2 broad categories. The first aspect of active control is the addition of a flow control valve. This type of control can be used to ensure that both wings fill at the exact same rate, despite a differing pressure along the span of the aircraft. In Flowmaster, we can accomplish this with the combination of a valve component, a gauge component to measure the flow, and a proportional controller to feed the valve with an opening signal. The other aspect of active control in our model is flow scheduling. Here, we use the logical rules defined in a custom script inside a controller component to route fuel from the refueling lines into the tanks in the specific order we desire. In our case, we want to simultaneously fill the wing tanks first and the center tank last. Finally, we want to be able to stop at any total amount of fuel we desire in order to keep the aircraft weight to a minimum on shorter flights. Let's look at how the flow control valve assembly works in detail. The key component is, of course, the valve itself. By applying an opening signal, we can position the valve at any value we want to restrict or allow flow. A gauge is added to the outlet arm of the valve to measure volumetric flow rate in real time. This component provides immediate feedback to a P.I.D, or Proportional Integral Derivative Controller. This controller applies the P.I.D function to compare a given input signal to either a constant or variable setpoint signal to achieve a desired outcome. The first term in the function is the proportional term. Here, the normalized difference in signal and setpoint, called the error, is multiplied by a proportional constant. This term is added to the second term, the integral. Here, the integral of the signal with respect to time is multiplied by the integral constant. The sum is then combined with the final term, the derivative. Here, the derivative of the error with respect to time is multiplied by the chosen derivative constant. The sum of all three becomes the output of the P.I.D component and is passed through a controller template onto the valve. This final controller is usually not needed for a simple flow control valve, but here it serves as an on-off switch and gives us a convenient way to override the P.I.D to totally close or open the valve if desired. Now that we know how the P.I.D function works, we need to know how we can easily determine good values for our proportional, integral, and derivative constants. There are entire papers and graduate-level coursework devoted to P.I.Ds and tuning, but for our purposes, we have two main methods that give reasonable results. The first is simple trial and error. With trial and error, you first increase the proportional constant until you get a reasonably fast, stable result. Then add integral constant to dampen out any unwanted oscillation. The integral term can cause the output to overshoot the set point, so then adding to the derivative constant can help eliminate that overshoot. This method can be quite cumbersome, so there's another method that helps you arrive at a reasonably good solution with less manual iteration. The Ziegler-Nichols tuning method. With this method, a critical gain is identified by increasing the proportional constant until oscillation is observed. The period of this oscillation is also noted. Based on the critical gain and that period, a set of P, I, and D values can be determined by taking 6/10 of the critical gain as the proportional input, 1/2 of the period as the integral, and 1/8 of the period as the derivative constant. Applying the Ziegler-Nichols method to our system, we can increase the proportional constant alone from 1 to 2 to 3, and lastly 3.5. Oscillation begins with the proportional constant set to 3, and the period of the oscillations for that value is a little less than about 0.125 seconds, so we will use that value for a rough estimate. After running our study, we identified a gain of 3 and a period of 0.125. Plugging that into the Ziegler-Nichols tuning functions gives us final proportional constants of 1.8, an integral constant of 0.104, and a derivative constant of 0.0156. And the result, when tested, is a very stable and accurate response from our P.I.D, straying from our desired set point by a very small amount. After tuning our P.I.D, we can return to the rest of the flow control system by adding our on-off control. To drive our controller-based on-off switch, we need some sort of control logic. For this task, we'll use a component called the master controller. The master controller is a template component, meaning it is meant to be customized to take whatever constant, curve, or three-dimensional surface map data that you have. These data are accessed via a script written in VBA, JavaScript, or in this case, C#. These scripts can easily be written to apply if-then logical statements to read gauges, compare them to some condition, and send an outcome to a controller. In this case, the script is sending a valve opening signal to a valve component. We configured the model for refueling mode, starting with empty tanks. After running a transient simulation, we can look at some simulation results to show what our active controls did for us. Here, you see a plot of tank inlet valve opening versus time for the left, right, and center tanks. Because of a difference in pressure from left to right across the aircraft, we need a larger valve opening for the right tank to get an equal flow rate. Here, you'll notice that our flow control valve for the right side, in red, is open approximately 15% more than the left-hand side to achieve the same flow rate. Additionally, over the course of the refueling event, the tanks are filling and providing some resistance in the form of additional head. As the tanks fill, the valves on both sides open by an additional amount to maintain flow. At approximately 550 seconds, the left and right wing tanks fill completely, so the active scheduling of the master controller and its script cause those flow control valves to close and the center tank valve to open to 100% to fill that tank at a maximum possible rate. Since balance is not an issue for the center tank, the flow control valve is not used. Here is a plot of volumetric flow rate as a function of time. You can see the perfect overlap of the left and right flow rate locked to our desired set point of 250 gallons per minute on each side. Once the wing tanks fill and the center tank valve opens, that tank fills at around 300 gallons per minute. Because of the lack of active control on the center tank, the effective head rise as the tank fills is seen as a small but measurable reduction in flow rate. Lastly, we can look at the mass of fuel in each tank as a function of time. Here again, we don't see any difference between the mass in the right or the left-hand tanks. Thanks to our active flow control, we can ensure that as we refuel, we pose no danger to the lateral balance of the aircraft. In this example, the desired amount of fuel was set to 50,000 pounds total, and we can see that after the wing tanks filled to 15,000 pounds each, and the center tank filled to 20,000 pounds, for a total of 50,000 pounds, the scheduling provided by our master control script closed the refueling valves automatically. As we showed in the previous presentation, the problem of unbalanced flow during single-sided ground refueling can only partially be solved by adding flow restrictors and increasing pipe sizes. In both cases, each change also introduces unwanted side effects like excessive line pressure, packaging, and weight issues. By adding active control and using a combination of all of these methods, we can achieve perfectly balanced flow at a sufficient overall flow rate at a reasonable pressure and line size. With active control, we also gain the ability to effectively track and control the total amount of fuel we put on board. This has major efficiency benefits by enabling the aircraft to fly with only the amount of fuel it needs for a given mission, saving weight. For the next case study, let's look at another benefit of active control, the automatic routing and distribution of fuel during the course of an entire flight or mission. In flight, it's often advantageous to maintain as high a fuel load in the wings as possible. The weight in the wings is supported by the entire length of the wing and not cantilevered off a large lever arm as it would be if stored solely in the fuselage. Furthermore, the added mass in the wings gives a larger inertia, which can help the whole aircraft stability during turbulence. A significant amount of fuel is still stored in the center of the fuselage, but in most aircraft, the engines are on the wings and draw fuel directly from the wing tanks. We need to design a way for fuel in the fuselage to get to the engines in a safe and efficient manner. We could use control valves and scheduling to change the point of engine supply from the wing tanks to the fuselage tanks, but this method could make piping and valve control more complicated and could potentially lead to a situation where the valves could fail and starve the engines of fuel. Therefore, we're going to design an active control method to periodically resupply the wing tanks to keep them in a mostly full state for as long as possible over the course of a flight. Here again is our fuel system model. And here is how the fuel moves from our wing tanks through a pump to the engines. As the fuel is depleted, we would like to refill the tanks by pumping fuel from the center tank into the refuel gallery and into the wing tanks, just as in the ground refueling case. In our design, we won't let the wing tanks go completely empty, but periodically refill by a small amount, several times over the course of the flight. We want to strike a balance between continuous pumping and maintaining a high enough mass in the wings for as long as possible. To accomplish this, we're going to again need the help of active control. In this scenario, we're solely going to look at the logic required to achieve the fuel routing we require. Again, we'll leverage the power of Flowmaster scripting to apply logical if statements to move fuel from the center tank out to the wing tanks automatically over the course of a flight. We'll specify upper and lower set points, and control pumps and valves will actuate automatically to maintain the fuel between those points. Should the center tank become completely empty, we'll allow the fuel in the wing tanks to go below the lower set point to utilize all the possible fuel on board. Again, we're going to use a master control to drive our scheduled flow of fuel from one tank to another. We can leverage the customizability of the controller to add custom data fields for upper and lower fuel set points within the tank. Just like in the previous example, our controller, via its script, can access values recorded by gauge components and pass the output of the script logic to controllers attached to the valves and pumps in the model. The controller script can then access those parameters as conditions in the if-then logic. The script directly accesses the gauges in the model to access the current mass of fuel in each tank and compare that to the upper and lower set points that we entered on our customized master controller. Depending on if the mass is above the upper set point or below the lower set point, the script sends value positions and pump speeds to the relevant controllers in the model. For our model to reflect reality, we also need to have an accurate flow of fuel from the tanks to the engines. To simulate a flight, we can add mission profiles to our control script and apply a dynamic change of flow rate, altitude, airspeed, pressure, temperature, or any other relevant variable we want in the form of a constant set point, a curve, or a surface map. For this simulation, we've only included curves of altitude and fuel flow rate versus time for simplicity. In our script, it's straightforward to read and apply these curves with a single command for each. We just feed simulation time into a function and either get altitude or engine flow rate as a result parameter that we can then apply elsewhere in our script. Here's a closer look at our actual flight profile. This is our plot of altitude versus time. It shows a fairly straightforward flight from point A to B. After a takeoff and climb, the aircraft cruises for just under 2 hours and then descends to landing. Overlaid on the altitude plot is the engine flow rate as a function of time. Here, changing flow rate for takeoff, climb, cruise, descent, and landing are all represented as steps and gradients on the plot. After running the simulation, we can overlay a plot of total fuel on board on top of our engine flow rate plot. Here, it's simple to see that when the flow rate to the engines changes, the slope of the total fuel curve does as well. We can also see that for a several-hour flight, we burn just over 10,000 pounds of fuel. Here is a plot of the individual tank mass for the same flight profile, where we started with an initial load of about 50,000 pounds. We can superimpose the 15,000 and 14,000 pound upper and lower wing set points of the wing tanks over the plot so you can see the periodic transfer of fuel from the center tank out to each wing. With this amount of fuel, the center tank never goes dry, which means that the wing tanks always stay mostly full for the entirety of the flight. However, in this case we carry excess fuel and don't get a good depiction of how our control script handles the complete depletion of the center tank. With that in mind, we repeated the flight, but in this case, with only 35,000 pounds of fuel on board. Here, again, you can see that the wing tanks are replenished periodically from the center tank, but this only occurs twice before the center tank is emptied and the fuel continues to drain from the wing tanks below the lower set point that we set. You'll notice that the center tank does not go completely empty, but stops with several hundred pounds of unusable fuel remaining. This is a capability we designed into our model as part of the control script, and this cutoff point can be adjusted to reflect the true conditions of the aircraft as the design progresses. In this example, we showed how active controls, including a pre-scripted flight profile, could be applied to the model to simulate a complete flight and help achieve our goal of maximum fuel storage in the wing tanks while avoiding complicated piping or opening the design up to single points of failure, such as single isolation valves. The periodic resupply is designed to strike a balance between continuous pumping and a constant fuel level in the wings. Hopefully, you've learned that adding controls can add significantly more capability to your models and let you simulate and analyze both simple situations and very complex control behavior.